Hi everyone, today we are going to answer this question posted at the ROS Answers forum that is asking about how to include a rotational axis into the Turtlebot. When the person, he means that how to add a rotational axis to the Kinect sensor camera of the Turtlebot, of course. So like making the Kinect be enabled to turn to one direction or another. So let's have a look at how to do this. And for this, we are going to follow the same procedure as we did on a previous video, number 70, about moving joints in gazebo, with a very simple example that was about a simple robot with two links and one joint, and then we made it rotational, this joint, so we allow to rotate. So we are going to do the same example, but now for the Turtlebot robot and the Kinect. Okay, so for that, let's go and launch the Turtlebot simulation. For this, I'm going to use the ROS Development Studio, and inside here I have created already a project, Turtlebot Rotating Kinect, that basically contains the simulation of the Turtlebot robot. So I'm not going to show how to do this, already explained in previous video. If you want to download this yourself at the ROS Development Studio, for example, or your own computer, you can go to our repository that is public, and then here you can find the simulation of the Turtlebot that works for this purpose. So I have already cloned it and created this project. I have created the project and cloned it, so it's ready. So we only need to open. You can follow the same steps as I am doing at the ROS Development Studio by creating a free account, and then you can follow. So let's open it, and then once it opens, I'm not going to restore, so fresh open. Let's see first the simulation. For that, I'm going to open the IDE here, Cloud9, and here we have some previous file, so let me put it bigger, and here I don't know, I'm going to close. So here we have three different workspaces: Kaki, notebooks, and simulation. The one that we are going to use is the simulation because it's there where our simulations are located. In this case, it's the Kabuki Turtlebot simulation. Great. So first, before anything else, let's launch that simulation and see how it looks. For that, I'm going to simulations, and I'm going to launch my own simulation from the simulation space. So I'm going to select this option and now select the launch file that launches that simulation. I know that is within the Turtlebot Gazebo main launch. So let's launch it and let's see how it opens. I'm going to put it here. Remember that you can follow all those steps if you log in into the ROS Development Studio, that address here, and create a free account. And you only need a web browser, so you can do all those steps with any computer, Mac, Windows, Linux, whatever. So here we have the simulation, and here we have the Turtlebot, and we have here the Kinect. Actually is an ASUS device, but basically it's the same device. So here it's what we are going to add a joint here. Okay, so we allow the Kinect, the ASUS, to rotate to one side, to one direction or the other. So like looking to the left and to the right. Great. For that, how do we do that? So by adding a joint into that link. And so I have already started the simulation, and the Kabuki simulation is quite complex, so I know where we have to modify. Okay, so I'm going to tell you straight, but otherwise you will have to look for this joint here that is already defined into the URDF. So I'm going to tell you as straight where it is, and it is on a file that is inside the Kabuki description URDF directory, sensors, and then it's called ASUS Axion Pro Chakro. So if we open this, here we have the whole simulation, the whole file that defines all the things, all the links and joints related to that camera. So what is the one that contains the Axion Pro? Is, as you can see, is very easy to see. It's this joint. This is the joint that connects the camera link to another link. to another link. And is the camera link the one that contains this Axion Pro Camera 3D description? So it means that this link is the one that contains the visual of the sensor. Okay, so this is the one that we have to connect using a joint that can rotate. So the joint that connects this is this one, the camera joint, but is of type fixed. So it means that it cannot rotate. So for that, what we have to do is to change into continuous. So let me change it to continuous type, so now it can rotate. And by having done this change, we also have to do another change, that is to specify the axis in which we want it to rotate. So in this case, okay, I have already specified that is not, this one is not correct, but this one. Okay, so it's the Z, because it's the axis that goes up on the sensor and allows to rotate to right and to the left. So here it is. And now we have to specify also another thing, because in order to make this type of joints work, both links, the parent and the child that this joint is connecting, both of them have to have the inertia parameters set. So in this case, the camera link contains those parameters, but the parent one, the camera RGB frame link, that is this one here, doesn't contain those parameters, the inertia. So what I'm going to do is very simple. You can try to calculate those values, but I'm not going to do it because it doesn't matter now for this specific simulation. So you can try to build this with a minimum amount of inertia and mass, etc. So I'm just copying the same values because that's how it works. And let's close with the link. So here we specify that is the link that is closed. Great. So what we have done here on the Asus Axion Pro is first to change the type of the joint that connects the previous stuff to the camera from a type fixed to a type continuous. Then we have provided the axis of rotation, and then also we have modified the previous link to have some inertia. Okay, so yeah, so here we have. Great, first thing done. So we have modified the URDF for including a continuous joint that can rotate. Next thing is to include the controllers into the URDF, so Gazebo knows how to do this, how to manage this. For this, we go to another file that is called the Kabuki description, also URDF, and then it's called Kabuki Gazebo. So here is where all the plugins for controlling the different sensors and wheels, etc., they are set up, and here is where we have to put our controllers for controlling that joint. And if you have a look at this video here, you will be able to see which controllers are. So I'm just going to copy and paste there and explain a little bit. Okay, so let me copy and paste. Okay, and that's it. Yes, so the first thing that we have to see is that we have to load the Gazebo ROS control, of course. This is the one that allows us to control the joints as a controller, and we set it into a simple model namespace. Then the second thing that we have to do is to change the transmission. So to add a transmission, that this is the one that specifies which type of controller is this joint going to use. This one, camera joint. Okay, great. So now we see here that are some different parameters here that you can check there on the previous video, but the important part is this one. Which one is the joint name, so it's called camera joint, and which one is the type of controller. Here it's called the effort joint interface. So now we have properly set up. Okay, next thing is, this is how the controller has to work. Sorry, this is which controller we have to load into the simulation, but now we have to create a configuration file for those specific controllers, so the simulation knows how, in which way it has to work this controller. For that, what we are going to do is to create here inside the Kabuki description a new folder that is going to be called config, and inside the config I'm going to create a new file, config.yam, that is a YAML file containing the configuration of that controller, and I have the code here already, so I'm going to copy and paste. Basically it's the subspace simple model as the one that we have specified here in the calling of the ROS control, and then we specify which type of controllers we are going to load. The first one is the joint state controller, that is the one that publishes the current situation, the current status of the joints, that it will be that joint there. And then the second one is the Kinect joint controller. This is a controller we call like that, so it's a name, only as a tag, but this is the one that it's going to be loaded of type effort joint position controller, as it is specified here. It's this one, effort joint interface, and which joint is going to control. In this case is camera joint, and also the PID values. So basically this is the camera joint that we have here and that we have here. Great, that is a type continuous. So by doing this, we already have configured properly the plugins that we are loading here. Okay, so almost done. The last thing that we need to modify is the launch file that is launching the whole simulation in order to tell it to load this config YAM and launch the controllers. So this is basically, it is on a file that it's called, it's on the source Kabuki Turtlebot gazebo, so it's here, Turtlebot gazebo, and launch includes Kabuki launch, is this one here. Okay, so here we have that. Wait. So let me put it bigger so we can see better. Great, so here is where we are loading the whole model. You see, we are loading the URDF file into the param server, and then we are spawning it into the simulation. Great, so here is where we have to load the controller. So after we have spawned it, we are going to load the joint controllers here, and let me show you how it looks like, the code here. Yeah, so I have copied here. First, we load into the param server, we load the config file that we have created. Okay, so this is just loading our config file, the one that we have created here. Great. Now, once we have this, we call the controller manager and we say to spawn into a namespace simple model the joint state controller and the Kinect joint controller. Those two are the labels that we have defined here, config YAM, joint state controller and Kinect joint controller. So we are indicating here with this sentence, hey, please spawn those controllers. That's it, just with a shutdown timeout of 3, but this is optional. So we are indicating to spawn the two controllers. So by doing this, then we'll have the controllers controlling that joint. Okay, one final thing is to go to the main launch. The main launch is the one that I have selected to launch the simulation, if you remember. It's this one. I'm going to change to type XML. Yeah. And here we need to publish the state of the joins into the robot state publisher. And for that, since we have created this namespace simple model, we need to modify a little bit this main launch. It's already been launched at the robot state publisher, but we have to add a remap from the joined states to the joint states on the namespace that we have selected. So basically it's a remap from joint state to simple model joint states. Okay, there it is. So we have everything already configured. So let's relaunch our simulation and see how it looks. If we do have this control. For that, I'm going to again select launch file and select the main launch file. So if I haven't done any mistake on the files, that is possible because I always commit some mistakes. So everything should load properly, load the controllers. It looks like it's loading the controller, so it looks like everything is going okay. So let's see. And there it is, the simulation. Okay, so you can see nothing different because the controllers just load the controller and the joint is there, so it's nothing physical that you can see. But how can we test this? Very simple. Let's open a shell and let me issue some command. So for example, let me check the topics that we have. And here we have this simple model joint states and simple model Kinect joint controller command. So this is supposed to be the topic to send commands to that joint. So let's launch, let's do an info of this topic. Let's see what it contains. Simple model Kinect joint controller command. And then it says it's a standard message, a float 64. That 64 is the position, because if you remember here, the controller is an effort controller in joint position controller. So it means that it's accepting positions as commands. So let's send a position to that topic, ROS topic, boop, at the simple Kinect command. Is of type std messages float, and let's say for example 0.5. So now, okay, something, oh yeah, so I didn't specify float 64 0.5. So now this should rotate to reach that position. There it is. Okay, great. So we have it. So we can also do we can check if this is looking properly by opening the RViz. So for that, let me open another shell and launch the RViz. And once this I have launched it, then I need to open a new tool that it's called the graphical tools. The graphical tools is the window that allows us to see any X Windows tool, like in this case is RViz. So here it is, RViz showing us the sensor, how it is rotated, and if we approach this way, yeah, we should be able, okay, there it is. Yeah, it's the point cloud that is very heavy, so it's showing us in the direction of the camera. And for example, if we rotate again to the 0 position, we should see on RViz how this changes. So now it has changed the position here of the sensor also in RViz, and also the perception of the camera. Okay, and here you have in the simulation also the rotation and the status. So that's it, basically how you do that. So remember that you can have more videos like this, and every day we are publishing new videos, so please subscribe to our YouTube channel. And if you want to learn more about ROS, we have an academy that is an online academy, Robot Ignite Academy, that you can go there and learn online using an environment very similar to this one, so you don't need to install anything. We are waiting for you there for teaching you many interesting subjects like OpenAI, autonomous cars, drones, and also the basics, of course, like perception, manipulation, etc. So thank you very much for attending this video, and see you on the next one.